And now in this lecture we'll answer two questions. In the first question we'll find out the area of the radius of this circle, and in the second question we'll find out the area of this circle using two different methods. We start with the first question. In the drawing we have a circle, and this is the right triangle ABC. We know that this is angle ABC, that is the right angle. Side AB equals to 3 units in its length. Line segment AD also equals to 3 units in its length. This is line segment DC. This equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So here we can implement rule 25 in our drawing. Repeat quickly rule 25. According to rule 25, if from a common external point, point P, we draw a tangent PA, that is tangent to this circle at point A, and a line segment that is actually secant PC that cuts the circle at 2 points, B and C. So in this drawing, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can actually implement rule 25 in our drawing. Why? Because in our drawing, if we focus on this common external point, point C, from this common external point C, we have tangent CE, that is tangent to this circle at point E, and we also have secant CA, that cuts the circle at 2 points, D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement here rule 25. And according to rule 25, the following equation will be true, that CE square equals to CD times CA. Again, CE square equals to CD times CA. So write it down. CE square, that is the square of tangent CE, equals to CD times CA. Again, according to rule 25, if we focus on this common external point C, the following equation will be true, that CE square equals to CD times CA. This equation is the implementation of rule 25 in our drawing. CE is the missing tangent, so we leave it as it is. So CE square equals to CD. CD is 1 times CA. CA in total is CD plus DA. That is to say, CA equals to 1 plus 3, that is 4. So in total, we should find out that according to rule 25, CE square equals to 1 times 4, that is 4. So CE square equals to 4. Here we'll take a root out of this equation, and we get that CE, tangent CE equals to 2 units in its length. So actually, this is tangent CE, that equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy the right triangle ABC in a new page, and we will implement on it the Pythagoras theorem. The hypotenuse AC equals to 4 units in its length, AB equals to 3 units in its length, and side BC is the missing side. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle ABC. This is the curve from the original drawing. In this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I write it down. AC squared equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, it is 16. And it is equal to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we leave it as it is. So in total, we found out that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7, so 7 equals to BC squared. Here we'll take a root out of this equation, and we get that BC equals to the square root of 7 units in its length. So actually, this is side BC, that is equals to the square root of 7 units in its length. What is the length of the missing line segment? Line segment BE. From the drawing, it is very easy to see that BE equals to BC minus EC. So it is known BE equals to BC minus EC. So BE equals to BC. BC is square root of 7 units in its length. Minus EC. EC is 2. So in total we found out that BE equals to the square root of 7 minus 2 units in its length. This is line segment BE. That equals to the square root of 7 minus 2 units in its length. It is given us the question that this is point O, that is the center of the circle. So we'll join points O and E together by straight line. Point O is the center of the circle, point E is the point of the circle itself. Therefore OE is the radius of this circle. We define the radius of this circle as R, so O equals to R. the radius OE is equals to R. The radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, we will do another construction, that is to say, from point O, that is the center of this circle, we will draw perpendicular on AB. Again, from point O, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and side AB. This point is point L. By doing this construction, we created here quadrilateral OLBE. In quadrilateral OLBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-facing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4-facing angle must be equal to 90 degrees in its size. So inside quadrilateral LOEB, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we went to quadrilateral LOEB, it's a rectangle because it has 4 right angles. So already known, quadrilateral LOBE is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side OE must be equal to the opposite side LB. But OE is R, it is the radius of the circle, therefore LB must be also equal to R units in its length. What is the length of this missing line 7 AL? From the drawing, it is very easy to see that AL equals to AB minus LB. So I don't know, AL equals to AB minus LB. So AL equals to LB. LB is 3 according to what is given as the question. Minus LB. LB is R. So in total, we found out that AL equals to 3 minus R units in its length. This is side AL, this is equals to 3 minus R units in its length. So, in rectangle LOEB, side BE must be equal to the opposite side LO, but BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. So, that is known. The opposite side LO is also equal to the square root of 7 minus 2 units in its length. In the next step, we will join points O and A together by a straight line. point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, that is equals to R. In the next step, I'll copy the right green triangle ALO in a new page, and we will implement the Pythagoras theorem of this right green triangle ALO. Here by PT is the regression from Pythagoras theorem. So actually, this is the right green triangle A and O that are coming from the original drawing. In this right triangle A and O, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. So I write it down. AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and it is equal to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared plus LO squared. LO is 7, square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we found out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared is equal to 3 squared, that is 9, plus R squared minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we found out that R squared equals to 9 plus R squared minus 6R plus 0.417. So here we have R squared on both sides of this equation, so R squared gets cancelled. After cancelled R squared, in this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 0.417, that is 9.417 minus 6R. So in total we found out that 0 equals to 9.417 minus 6R. Here we will add 6R to this equation, and we get that 6R equals to 9.417. Here we will divide this equation by 6, and finally we get that the radius that we are looking for with this equation R is equal to 9.417 over 6 is 1.57 units. Repeat again, we found out that the radius of this circle R is equal to 1.57 units in its length. So we finished with the first question. In the next step, I will present to you the second question, And we'll solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. So in the drawing we have a circle. This is line 7 BC, this equals to 6 units in Islam. This is called BA, this equals to 13 units in Islam. This is line 7 CD, this equals to 18 units in Islam. Again, our task is to find out the area of this circle. So first of all, and we also know that those two angles, they are both right angles. Those two angles are defined as one-sided interior angles, and the sum of those two one-sided interior angles is equal to 90 degrees plus 90 degrees is 180 degrees. And according to rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, which again, according to rule 7, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between parallel lines. The sum of those two one-sided interior angles is equal to 180 degrees, and therefore, according to rule 7, they are located between parallel lines. That is to say, BA is parallel to CD. Again, BA is parallel to CD according to rule 27. So I want to know. So chord BA is parallel to line 7 CD according to rule 27. In the next step, we define the center of this circle. This point is point O. And we will draw perpendicular from point O, that is the center of this circle, to line 7 CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and line 7 CD. This point is point M. In the next step, we will extend the perpendicular OM by straight line until it touches chord BA. Repeat again, we will extend the perpendicular OM by straight line until it touches chord BA. And we will define the touching point of the extended perpendicular OM with chord BA. This point is point N. If we have two lines this is line A and this is line B, and we know that line A is parallel to line B, then the perpendicular from any point to line A will be also perpendicular to line B. Why? Because they are parallel to each other. The perpendicular to line A, this is the perpendicular to line A, will be also perpendicular to line B. That is to say, if we will extend the perpendicular to line A by straight line until it touches line B, then it will be also perpendicular to line B. Why? Because they are parallel to each other. And again, the perpendicular to line A is also perpendicular to line B because they are parallel to each other. According to the rule that I mentioned, the perpendicular to line 7 CD will be also perpendicular to chord BA because they are parallel to each other. But again, the perpendicular to line segment CD will be also perpendicular to chord BA because they are parallel to each other according to rule 27. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to what I've explained to you. Okay? So by doing this construction, we created quadrilateral BCMN. Inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, those 4 angles must be equal to 90 degrees in its size. So in quadrilateral BCMN we have 4 right angles, and according to 5, any quadrilateral that has 4 right angles must be this right angle plus a square. So we relate to quadrilateral BCMN as a right angle because it has 4 right angles. ON is perpendicular to chord BA. So ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line OM at point M? We have this angle that is a right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say, from point A, we will do perpendicular on line 7 CD. Again, from point A, we will do perpendicular on line 7 CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and line 7 CD. This point is point L. By doing this construction, we create here quadrilateral NMLA. In quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral MNLA, we have 4 right angles. And according to rule 5, quadrilateral MNLA is a right angle. So it has 4 right angles. Here we can implement rule 19. Repeat rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the moment we have a circle, point O is the center of the circle, and we have also, this is chord AB. And according to this rule 19, the perpendicular OM to chord AB bisect chord AB. Again, the perpendicular OM from the center of the circle, that is to say from point O, the perpendicular OM to chord AB bisect chord AB. That is to say, it divides chord AB into 2 halves. The first half is AM, the second half is MB, and of course AM equals to MB. So according to rule 19, the perpendicular from the center of the circle towards any chord, bisect the chord. We can implement rule 19 in our drawing. Why? Because in our drawing, from the center of the circle, that is to say from point O, we have perpendicular ON on chord BA. Again, from the center of the circle, that is to say from point O, we have perpendicular ON on chord BA. And according to rule 19, perpendicular ON bisect chord BA. Again, according to rule 19, perpendicular ON bisect chord BA. BA in total equals to 13. According to what is given in the question, therefore, the first half BN must be equal to 13 over 2, that is 6.5. The second half NA must be also equal to 13 over 2, that is 6.5. So, let's see, we should find out that according to rule 19, BN equals to 6.5. And the second half NA also equals to 6.5 units in its length. We already found out that quadrilateral, the upper quadrilateral BCMN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. In the next step, we'll focus on the lower rectangle NMNA. In the lower rectangle NMNA, the opposite sides are equal to each other. That is to say, side NA is equal to the opposite side ML, but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment? Line segment LD. From the drawing, it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. LD equals to CD minus CL. So LD equals to CD is 18 according to what is given as the question, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total LD equals to 18 minus 13, that is 5. LD equals to 5 units in its length. This is the short line segment ND, that is equals to 5 units in its length. In the next step, we will extend line segment DC by a straight line until it touches the circle. And we define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we created chord TD. This is chord TD. So now we can implement rule 19 on chord TD. Why? Because from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. Again, from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. And according to rule 19, the perpendicular from the center of the circle OM bisects chord TD. If OM bisects chord TD, it means that it divides it into two halves. The first half is TM, the second half is MD, and of course TM equals to MD. So right now we found out that according to rule 19, Tm equals to Md. Tm equals to Md according to rule 19. But MD in total equals to 6.5 plus 5. Again, MD in total equals to 6.5 plus 5, that is 11.5. So you can write here that MD equals to 11.5 units in its length. And from this equation, Tm equals to Md equals to 11.5. We will derive that Tm is also equals to 11.5. This is line segment Tm, that is equals to 11.5 units in its length. So from one side, Tm equals to 11.5. But from the other side, Tm also equals to Tc plus Cm. Again, Tm equals to Tc plus Cm. Tm equals to Tc plus Cm. So you know, from the other side, Tm also equals to Tc plus Cm. And from this equation, 11.5 equals to Tm equals to Tc plus Cm. We will derive that 11.5 equals to Tc plus Cm. So 11.5 equals to Tc. Tc is the missing side, so we leave it as it is, plus Cm. Cm equals to 6.5. Therefore, we substitute Cm in this equation by 6.5. In total, we get that 11.5 equals to Tc plus 6.5. Here we subtract 6.5 from this equation, and we get that the missing 97 Tc is equal to 11.5 minus 6.5 is 5. So this is the missing 97 Tc, that is also equals to 5 units in itself, exactly like LD. In the next step, we will extend line segment BC by a straight line until it touches the circle. And we will define the touching point of the extended line segment BC with this circle. This point is point Q. By doing this construction, we create actually two chords that intersect with each other. That is to say, we created chord BQ that intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So I write it down. We created two chords that intersect with each other by doing this construction. That is to say, we created chord BQ that intersects with chord TD This is called TD at point C. The intersection point occurs at point C. Repeat again. By doing this construction, we created two chords that intersect with each other. That is to say, we created chord QB that intersects with chord TD at point C. And whenever you have two chords that intersects with each other, you can implement rule 15. Repeat quickly on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, again, if chord AB intersects with chord CD at point O, then the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Why? Because, as I already mentioned before, we have two chords that intersect with each other in our drawing. Chord BQ intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation will be true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So I write it down. According to rule 15, TC times CD equals to BC times CQ. Then again, according to rule 15, the following equation is true, that TC times CD equals to BC times CQ. TC is 5, times CD. CD is 18 according to what is given as the question, and it is equals to BC. BC is 6 also according to what is given as the question, times CQ. CQ is the missing line segment, so we leave it as it is. So in total, according to rule 15, we should find out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and finally get that CQ, the missing line segment CQ, is equal to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is the answer element CQ, that is equals to 15 units in its length. In the next step, we will join points Q and A together by a straight line. So we join points Q and A together by a straight line. So in the drawing, we have, this is periangle QBA, that is equals to 90 degrees in its size according to what is given as the question, and periangle QBA subtend on chord QA. Again, periangle QBA subtend on chord QA. So here we can implement rule 5. Repeat quickly rule 5. According to rule 5, any periangle that is equals to 90 degrees in its size must subtend on the diameter of the circle. So in the drawing we have a circle. This is periangle MAN, that is equal to 90 degrees in its size, and therefore according to this rule, rule 5, periangle MAN must subtend on the diameter of the circle. And indeed, periangle MAN subtend on chord MN, that is the diameter of the circle. So according to this rule 5, any periangle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. When put in our drawing, we have perforated QBA that is equal to 90 degrees inside, and therefore according to rule 5, perforated QBA that is a right angle must subtend of the diameter of the circle. Perforated QBA subtend on chord QA, and therefore according to rule 5, QA must be the diameter of the circle. So maintenant, je found that chord QA is the diameter of the circle according to rule 5. QA is the diameter of the circle according to rule 5. We know that the diameter of any circle is twice as long as the radius. So if we define the radius of this circle as r, then the diameter QA equals to 2r. This is the diameter QA is equal to 2r. In the next step, I'll copy the big right angle QBA in a new pattern. We'll implement on it the parallel theorem. Side QB of the right angle QBA in total equals to 15 plus 6, that is 21. Side BA equals to 13 units in its length according to what is given in the question. And the diameter QA is also the hypotenuse QA is also the diameter of this circle, that is equals to 2r. So copy the right angle QBA in an equation. We will implement on it the parallel theorem. Here by PT is the abbreviation for parallel theorem. So actually, this is the right triangle QBA, that is according to what we are knowing. This right triangle QBA, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total we should know that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So in total we should find out that 4r squared equals to 610. Here we divide this equation by 4. We finally get that r squared equals to 610 over 4 is 152.5. So in total we should find out that r squared equals to 52.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Read again. The area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r squared is 152.5. So we substitute r squared in this expression by 152.5. And again that the area of our circle equals to pi times 152.5. Or in terms of numbers, it is 479.09 square units in its size. And then again, if you found out the area that we are looking for this question, that is the area of this circle, it is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we use some of the fields that we already found out in the first method. We already found out that this is line segment C cubed. This equals to 15 units in itself. This is the short line segment TC. That is equals to 5 units in itself. So we use those two things in the second method that we already found out in the first method. So in the drawing we have chord BQ intersects with chord TD at 90 degrees at point C. Again, chord BQ intersects with chord TD at 90 degrees at point C. And whenever you have two chords that intersect with each other at 90 degrees, you can implement rule 26. And therefore, we can implement rule 26 in our drawing. So first of all, I write it down. We have found out that in our drawing, chord BQ intersects with chord TD at 90 degrees. That is to say, they create with each other 90 degrees at the intersection point, that is point C. The intersection point occurs at point C. Repeat again. Chord BQ intersects with chord TD at point C, at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. Repeat quickly on rule 26. According to rule 26, rule 26 is true in any circle. So in any circle, if two chords A, B, and CD intersect with each other at 90 degrees at point O, then the following equation is true, that AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. Repeat again. chord AB intersects with chord CD at 90 degrees, it's point O. So whenever you have two chords that intersect with each other at 90 degrees, like here, you can implement rule 26. According to rule 26, the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. So, 4, all the requirements of rule 26 are satisfied, and therefore we can implement rule 26 in our drawing. According to rule 26, the following equation will be true, that TC square plus CD square plus BC square plus CQ square equals to 4R square. And R is the radius of this circle. Again, TC square plus CD square plus BC square plus CQ square equals to 4R square. So I write it now. TC square plus CQ square plus TC square plus BC square plus CQ square. We do it in order. BC square plus CQ square plus TC square plus CD square equals to 4R square. R is the radius of this circle. Okay, again, according to rule 26, the following equation is true. PC square plus CQ square plus TC square plus CD square equals to 4R square. This equation is the implementation of rule 26 in our drawing. BC is 6, therefore BC square is 6 squared, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 225, plus TC square. TC is 5, therefore TC square is 5 squared, that is 25, plus CD square. CD is 18, therefore CD square is 18 squared, that is 324, equals to 4R square. So in total we found out that 36 plus 225 plus 25 plus 324 equals to 4R square. 225 plus 25 is 250, and 36 plus 324 is 360. So in total we found out that 250 plus 360 equals to 4R square. 250 plus 360 is 610. So 610 equals to 4R square. Here we divide this equation by 4, and finally get that R square equals to 610 over 4 is 152.5. So if you found out that R square equals to 152.5. Our test is to find out the area of this circle. We know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R square. So the area of our circle must be equal to pi R square. But R square is 152.5. So we substitute R square in this expression by 152.5, and we get that the area that we are looking for in this question, that is the area of this circle, is equal to either pi times 152.5 square units in size. In terms of numbers, the area of this circle is equal to 479.09 square units in its size. So in both methods, found out actually that the area of this circle equals to either 152.5 pi square units in size, or in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the second method and the second question. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the radius of this circle. So in the drawing we have a circle. This is the right angle ABC. This is the angle ABC, that is the right angle. Side AB equals to 4 units in itself. This is line segment AD, that is also equals to 4 units in itself. This is the short line segment TC, that is equals to 1 unit in itself. Again, our test is to find out the radius of this circle. So first of all, we implemented rule 25 in our drawing. From the current standpoint, point C, we have tangent CE, that is tangent to the circle point E, and we also have secant CA that cuts the circle to points D and A. So all the requirements for rule 25 are satisfied, and therefore we can implement rule 25. According to rule 25, the following equation is true, that CE squared equals to CD times CA. Again, CE squared equals to CD times CA. And again, if you focus on the common standpoint point C, the following equation will be true according to rule 25. That CE squared equals to CD times CA. C is the missing side, so we leave it as it is. And it is equals to CD. CD is 1 times CA. CA is 1 plus 3, that is 4. So in total, we found out that CE squared equals to 1 times 4. 1 times 4 is 4, so CE squared equals to 4. Here we took out all of this equation and we found out that CE equals to the square root of 4, that is 2. So this is the short line segment, and this is a tangent CE, that is equals to 2 units in its length. In the next step, we implemented the Badamas theorem on the big right angle ABC. According to the Badamas theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AC equals to 1 plus 3, that is 4. AB equals to 3, and BC is the missing side. So actually, this is the right angle ABC that according to the original drawing. This right angle ABC according to the Badamas theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we need to sit it. So in total, we found out that 16 equals to 9 plus BC squared. Here we subtract the 9 from this equation, we found out that BC squared equals to 16 minus 9, that is 7. So BC squared equals to 7. Here we took out of this equation and found out that BC equals to the square root of 7 units in its length. So this is side BC, that equals to the square root of 7 units in its length. So what is the length of this line segment BE? BE equals to BC minus AC. Repeat again. BE equals to BC minus AC. So B equals to BC, that is square root of 7, minus AC. AC is 2. So in total, BE equals to the square root of 7 minus 2 units in its length. This gives us the question that point O is the center of the circle. So from point O, we join points O and D together for a set line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle itself, so OE equals to R. The radius of OE is equals to R, the radius of OE is 1 to point E, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this circle equals to 90 degrees, and this circle also equals to 90 degrees according to rule 1. In the next step, we did another construction. That is to say, from point O, that is at the center of this circle, we do perpendicular on AB. Again, from point O, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we created it for the other OL. BE. Inside quadrilateral or LBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth cylinder, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth cylinder must be equal to 90 degrees in its size. So inside quadrilateral LOEB, we have 4 right angles, and according to rule 5, quadrilateral LOEB is rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side OE must be equal to the opposite side LB. But OE is R, therefore the opposite side LB must be also equal to R unit in its length. Likewise, according to the sum rule, the sum rectangle LOEB, side BE equals to the opposite side LO. But BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. So what is the length of this missing line segment LA? From the drawing, the missing line segment AL, from the drawing is to see that AL in total equals to AB minus LB. AL equals to AB minus LB. So AL equals to AB, that is 3, minus LB, that is R. So in total, AL equals to 3 minus R. In the next step, we join points A and O together by a set line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equals to R. In the next step, I copy the green right triangle ALO in the equation. We implement the pathological form of this green right triangle ALO. So okay, this is the green right triangle ALO, this is according to the original drawing. This triangle ALO, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and it is equals to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we should find out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared equals to 3 squared, that is 9, plus R squared minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared will get cancelled, R squared. This side of the equation is left nothing, that is to say 0. While on the other side of this equation we have 9 plus 0.417, that is 9.417 minus 6R. So in total, we actually found out that 0 equals to 9.417 minus 6R. Here we added 6R to this equation and find out that 6R equals to 9.417. So here we divided the equation by 6 and find out found out that the radius of this circle, that is the radius that we're looking for in this question, is equal to 9.417 over 6, that is 1.57 units in its length. We found out that the radius R of this circle is equal to 1.57 units in its length. So finish with the first question. In the next step, I present to you the second question and solve the second question in two different methods. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is line 7 BC, this is equal to 6 units in its length. This is called BA, this is equal to 13 units in its length. This is line 7 CD, this is equal to 18 units in its length. Again, our test is to find out the area of this circle. So first of all, in addition, we know that those two angles are both right angles. Those two right angles are defined as one-sided interangles. The sum of those two one-sided interangles is equal to 180 degrees, and therefore, according to rule 27, they must be located between parallel lines. That is to say, BA is parallel to CD according to 27. Okay, again, because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, they must be located between parallel lines. That is to say, chord BA is parallel to line 7 CD according to rule 27. And again, chord BA is parallel to line 7 CD according to rule 27. In the next step, we define the center of this area. This point is point O, and from point O we go perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. In the next step, we extended the perpendicular OM by side line until it touches chord BA. And we have the rule that if we have line A, if line A is parallel to line B, so we know that line A is parallel to line B, then the perpendicular to line A will be also perpendicular to line B. Again, if two lines are parallel to each other, the perpendicular to the first line will be also perpendicular to the second line. Again, line A is parallel to line B, so the perpendicular to line A will be also perpendicular to line B. BA is parallel to CD, and therefore the perpendicular OM will be also perpendicular to BA. The perpendicular OM to CD will be also perpendicular to BA. That is to say, ON is also perpendicular to BA. Okay, so this angle equals to 90 degrees, and this angle also equals to 90 degrees according to what I already explained to you. So, by doing this construction, we can do quadrilateral BCMN. Inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth incident angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth incident angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN we have 4 right angles, and therefore according to rule 5, quadrilateral BCMN is a rectangle. ON as a perpendicular, it is absolutely straight line. So if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have the lower side of ON at point M, we have this angle that is 90 degrees according to our construction, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we did another construction, that is to say, from point A, we do perpendicular on CD. Again, from point A, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we created the lower quadrilateral MNLA. Inside the lower quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of these 4 pieces again, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So inside the quadrilateral MNLA, we have 4 right angles, and therefore, according to rule 5, quadrilateral MNLA is a rectangle. Because it has 4 right angles. So in conclusion, we shall find out that those two quadrilaterals, they are both rectangles. So here, we can implement rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. Again, the perpendicular from the center of the circle towards any chord bisect the chord. So according to rule 19, the perpendicular ON to chord BA bisects chord BA. Again, the perpendicular ON from the center of the circle, that is to say from point O, the perpendicular ON bisects chord BA. That is to say, it divides chord BA into 2 halves. BA in total is 13, so the first half is 13 over 2, that is 6.5. The second half is NA, that is also 13 over 2, that is 6.5 in its name. So in rectangle BCMN, the opposite sides are equal to each other. So BN equals to CM. BN is 6.5, therefore the opposite sides CM must be also equal to 6.5 units in its name. Likewise, in the lower rectangle MNLA, and side NA equals to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length from this? This is 97 LD. LD in total equals to CD minus CL. Again, CD minus CL equals to LD. Repeat again, LD equals to CD minus CL. So LD equals to CD, this is 18, minus CL. CL in total is 6.5 plus 6.5, that is 13. So in total LD equals to 18 minus 13, that is 5. So LD equals to 5 units in its length. In the next step, we extended 97 DC by straight line until it touches the circle. We define the touching point of the extended 97 DC with this circle. This point is point T. By doing this construction, we created chord TD. Again, by doing this construction, we created chord TD. So now we can implement rule 19 on chord TD. According to rule 19, the perpendicular from the center of the circle, that is to say from point O, perpendicular OM bisect chord TD. Again, according to rule 19, the perpendicular from the center of the circle, that is point O, the perpendicular OM bisect chord TD. That is to say, perpendicular OM divides chord TD into 2 halves. The first half is TM, the second half is MD, and the first half TM equals to MD. So TM equals to MD according to rule 19. And again, according to rule 19, TM equals to MD. But MD in total equals to 6.5 plus 5, that is 11.5. Okay, now I tell that MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we derive that TM is also equals to 11.5 units in its length. This is 97 TM, this is equals to 11.5 units in its length. So from one side, TM equals to 11.5. From the other side, TM also equals to TC plus CM. Again, TM equals to TC plus CM. So from the other side, TM also equals to TC plus CM. And from this equation, 11.5 equals to TM equals to TC plus CM. We will derive that 11.5 equals to TC plus CM. So 11.5 equals to TC. TC is the missing side, so the limit is it is plus CM. CM equals to 6.5. So we substitute CF by 6.5. In total, we found out that 11.5 equals to TC plus 6.5. Here we subtract the 6.5 from this equation, and finally found out that the missing 97 TC equals to 11.5 from 6.5 is 5. This is the missing 97 TC, that is equals to 5 units in its length. In the next step, we extended 97 BC by a straight line until it touches the circle. And we define the touching point of the extended 97 BC with this circle. This point is point Q. By doing this construction, we created two chords that intersect with each other. That is to say, chord BQ intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. And whenever you have two chords that intersect with each other, you can implement rule 15. So according, repeat again, chord BQ intersects with chord TD at point C. So all the requirements for rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation is true that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. TC is 5, CD is 18, BC is 6, CQ is the resistance of electricity. So in total, we actually found out that 5 times 18 equals to 6 CQ. Here we divided this equation by 6 and finally found out that CQ equals to 18 over 6 is 3, and 3 times 5 is 15. So this is 97 CQ, that is equals to 15 units in its length. In the next step, we join points Q and A together by a straight line. By joining points Q and A, we can here peripheral angle QBA. Peripheral angle QBA equals to 90 degrees in size, and it's subtend on chord QA. So we can implement here rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size, like this peripheral angle QBA, must subtend on the diameter of the circle. So peripheral angle QBA equals to 90 degrees in size, and therefore it must subtend on QA, that is the diameter of the circle. So therefore QA, peripheral angle QBA equals to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Peripheral angle QBA subtend on QA, and therefore according to rule 5, QA must be the diameter of the circle. Okay, QA is the diameter of the circle according to rule 5. QA is the diameter of the circle according to rule 5. The diameter is twice as long as the radius. So if the radius is r, then the diameter QA must be equal to 2r. In the next step, I commit the right target QBA in the equation. We implemented the Pythagoras formula on this right triangle QBA. QB equals to 15 plus 6, that is 21. BA equals to 13, and QA, the hypotenuse QA equals to 2r. It is also the diameter of the circle. So this is the right triangle QBA, that is comes from the original domain. This right triangle QBA, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA squared is BA is 13, therefore BA squared is 13 squared. So in total, we should find out that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So 4r squared equals to 610. Here we divided this equation by 4 and found out that r squared equals to 610 over 4, that is 152.5. So r squared equals to 152.5. Our task is to find out the area of the circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. Therefore the area of our circle must be equal to pi r squared. But r squared is 152.5. So we substitute r squared in this expression by 152.5, and finally found out that the area of this circle, that is the area that we are looking for in this question, is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle is equal to 479.09 square units in size. So we finish with the first method. In the next step, we have to find out the area of this circle using second method. In the second method, we used with the things that we only found out in the first method. In the first method, we only found out that line symmetry Q equals to 15 units in SEM, and this is line symmetry C, that is equals to 5 units in SEM. So use those two things in the second method. So in the drawing we have chord QB intersects with chord TD 90 degrees at point C. Again, chord QB intersects with chord TD 90 degrees at point C. And now you have two chords that intersect with each other at 90 degrees. You can implement rule 26. Repeat again. Now what you are doing, chord QB intersects with chord TD 90 degrees at point C. So according to rule 26, the following equation is true that TC square plus CD square plus BC square plus CQ square equals to 4R square. And now is the radius of the circle. And again, according to rule 26, the following equation is true that BC square plus CQ square plus TC square plus CD square equals to 4R square. BC is 6, therefore BC square is 6 squared, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 125, plus TC squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, and it is equals to 4R squared. 225 plus 25 is 250, and 36 plus 324 is 360 equals to 4R squared. 250 plus 360 is 610, so 610 equals to 4R squared. Here we divided this equation by 4 and find out that R squared equals to 152.5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the area of the circle squared. The area of our circle squared. But the area of our circle squared is R squared, so the area of our circle must be equal to pi R squared. But R squared is 152.5, so we substitute R squared in this expression by 152.5, and find out that the area of this circle, that is the area that we are looking for in this expression, is equal to either 152.5 pi square units in size, so in terms of numbers, the area of this circle equals to 479.09 square units in its size. So in both methods, we arrive to the same result. The result is, so we mentioned before, that the area of this circle equals to either 152.5 pi square units in size, or in terms of numbers, the area of this circle equals to 479.09 square units in its size. Okay, thank you very much.